So far, we've been hearing a lot about how weight is a huge issue when you want to fly something. And of course, the structural integrity and safety of the craft is important as well. Now, in the past, to compensate for safety, vehicles were generally made much heavier than needed. This was due in part to a lack of understanding about certain structural test failures, like buckling. Today, researchers have a much better understanding of the buckling process and the fine balance between weight, safety, and performance in vehicle launch design. For spacecraft design, researchers are using a technique to test shell buckling that will help them better understand this balance. I spoke with Mark Hilberger here at NASA Langley to find out a little more. So Mark, why is NASA testing shell buckling?
Well, shell buckling is one of the primary failure modes that we have in launch vehicle structures. And what we're doing today is trying to revise some old design guidelines that NASA generated a long time ago for the Apollo era. And why it is critical is if we are building structures too heavy, like we have in the past, we're not going to be able to get the payload into space like we want to. So we're studying here the fundamental physics of buckling and then trying to apply that to an updated design criteria that will allow us to make us lighter weight, more efficient, safe launch vehicle structures. I've got a little test I can show you. This is a typical beverage can, and we've all crushed these before under our feet, I'm sure. And what we mean by a thin shell is that it has a very thin wall and it's shaped like a cylinder. And if you could picture this as being much bigger and used in a launch vehicle as like a fuel tank or something like that, they're subjected to very high loads. And one of the problems that we're studying is how do these cans buckle so we can design better launch vehicle structures. So I'm just going to turn this screw and apply a load, a compression load on this can, and I'm going to try and make this buckle. Oh.
Pretty immediate.
Yeah, it's pretty immediate and catastrophic.
3, 2.
Launch vehicles are also cylindrical structures like these with thin walls. They have all the same basic physical response characteristics that a can would have. And so when they're subjected to the load, they can also exhibit catastrophic buckling failure. When they were first trying to develop rockets right after World War II and you see them going up on the launch pad and then they just crumble, that was a buckling problem. The buckling phenomenon itself is when you're applying a compressive load to a structure and it can no longer withstand that load, and so it causes the can's cross-section to crush inward. So it's imperative that we understand the buckling process. That obviously was a very simple example, but what I have behind me here is a smaller laboratory scale test article that we would use to understand some of the basic physical principles of shell buckling and try and apply that to understanding larger structures. So what we have here is a small scale structure. We're studying various aspects of how it buckles, the effects of geometry and different types of load on the buckling behavior. You can see there's all sorts of instrumentation on here, so we're much more scientific than just crushing the can.
In a vice grip, right.
Yeah,
right.
So we then take that data and use that to compare to our models to see how well we really understand the process.
All right, in addition to the wires and the things I see attached, I see little tiny dots.
Yeah.
What are they there for?
Well, many years ago, NASA started working with some universities to develop what we call a video image correlation system. And what it is it's a series of digital cameras that we position around the circumference of the shell, and it monitors this speckle pattern that we've painted onto the shell. And during the test, as we're loading it, it's monitoring the movement of the shell wall.
The slightest movement will be picked up.
Sub-millimeter movements. And the really nice thing is, what you see here is a laboratory scale. We're down at Marshall also testing full launch vehicle size structures. We use the same technique, we just use bigger dots.
Mark, what's the difference between the testing, the shell buckling testing they did on Apollo, and the shell buckling testing you guys are doing right now?
Oh, that's a great question. And back in the Apollo era, they were just starting to understand sort of the fundamental physics of the buckling process. The best thing that they could do is run a lot of tests, but not really get a handle on the real physics. But they did a great job because they got to the moon.
Right.
What we're doing now, though, is we're applying more rigor to how we run our tests, the types of measurements that we take. We have new measurement technologies, we have new analysis tools that allow us to very accurately predict the behavior of these shells.
It's always increasing technology, huh?
Absolutely. It's hard to keep in front of it.
I know it is. You're doing a great job. Thanks so much.
Thanks.
Because composites are being used more and more in passenger vehicles like cars and planes, NASA researchers are taking a hard look at how they can make them more robust. Now, as they become more robust, they still have to maintain some of the benefits that composite materials have to offer, like weight reduction. Yeah, this is a tough task, but NASA researchers, well, they're up for the challenge.
I caught up with NASA aerospace engineer Don Jegley to find out more about this new design called Perseus that may be a game changer in composites research.
Don, how are you?
Hi, how are you?
Good to see you.
You too.
Good. So we're here today to talk about composites and Perseus, right?
Right.
Let's start from the top.
Okay, well, Perseus stands for Pultruded Rod Stitched Efficient Unitized Structure.
Okay.
What that means is that we have a large panel, and this is a Perseus panel.
Right.
And if you look real close in here, you can see stitches. It's all held together by stitches. And what you'll notice when you look at this panel, rather than a normal aircraft panel, is you don't see any fasteners. In a normal airplane, you've got rivets all over the place holding every part together. In this case, we have no rivets.
Right.
Everything's held together by stitches.
Okay.
Now, composite materials have been around for a long time. We at NASA have been working with them for 40 years. Industry's working with them, and they're now getting out into real aircraft structures.
Gotcha.
But what's different about Perseus is a couple things. First of all is the stitching. Composite materials, composite structures are put together using layers of graphite epoxy or carbon epoxy materials that's all built up into whatever configuration you're looking for. With Perseus, what we're trying to do is build very large unitized structures. So we can get away from all those fasteners by putting in the stitches and by making very large parts. So composites are useful. Composites are good because they're lighter weight than aluminum. With lightweight structure, you can cut down on your fuel costs. And of course, one of the things NASA's looking at today is reducing the amount of fuel that's used and producing less pollution. So we're looking at the next fleet of aircraft would be lighter and more fuel efficient.
What are you doing with this piece?
Okay, this panel was fabricated by Boeing. We're going to do the testing here, and what we're going to do with it is we're going to put it in this test machine, so we're going to slide it back.
Right.
We're going to take the platen here, raise it up, put the panel underneath it, and then position the platen so that it's just at the top of the panel.
Okay.
Now, this machine can apply up to 1,000,000 pounds of loading. So what we're going to do is bring the platen down to the surface of the panel and then slowly apply load to push the panel down.
Okay.
While we do that, we're going to monitor the behavior of all the strain gauges here to look at what the panel's feeling, and we're going to have additional measurements. So we're going to look at the displacements, how the panel moves in a couple different directions during the test. So what we're going to try to find out is how the panel behaves while we're pushing down on it, and then we're going to take it to failure. And what's going to happen is we're going to get a failure somewhere in the panel, probably somewhere in this region here.
Okay.
And what's going to happen is we'll see what the failure load is and where it starts, and then we'll take a look at all the instrumentation we have and compare that to our analysis. Because right now we have an analysis of the panel, but the reason that we have to do the testing is we have to make sure our analysis is right. And because composites are a lot newer than aluminum, and particularly Perseus doesn't have that much of a database to draw from, we have to do a lot of testing to make sure we really understand the behavior. Because you wouldn't want to put this kind of structure on a real airplane unless you can predict its behavior. And that's what NASA's been trying to do with Boeing, is develop the technology to really understand that behavior so we can predict it.
Well, good luck on the test.
Thank you very much.
Definitely, and we hope to see this on a future airplane.
So do I.
Right on.